So this video covers section 9.5 from your text, and we are going to be talking in this section about two main concepts. The first is how do we solve equations that have square roots and cube roots and things like that in them. And then once we learn how to do that, we are then going to apply that skill to solving some application problems that involve square roots and so forth, or radicals. So just as a review, I want to remind everyone that when we talk about inverse operations, the operation that undoes a square root is the operation of squaring. So if I have the square root of a and I square it, the square gets rid of the square root, leaving us just a. And this is the main tool that we're going to use to help us solve radical equations. And so I have here, when I'm solving radical equations, I have basically a four-step process. And I mean, you can follow these steps to help you solve the problem, but really I want you to focus in on what it is that we're doing, because that's going to be the key to helping you actually solve these. So the key step, first step here, is to isolate one radical on one side of the equation if necessary. I say one radical because there are sometimes the case where we have more than one radical. But the key step here is to isolate. If you don't isolate first, you're going to get into all kinds of trouble. And this should sound familiar to you because we did this before when we solved absolute value equations and inequalities. So we should be used to isolating. For this particular problem, if we were going to isolate, we would of course start out by adding 12 to both sides. And when we do that, we end up with 8 times the square root of x plus 5 equals 40. And then we still don't have the square root by itself, so what would our next step be? We would need to divide both sides by 8. And so then when we divide both sides by 8, the 8's cancel over here, so we have the square root of x plus 5. And then of course 40 divided by 8 is 5. And so now we have the radical isolated. This is our, basically everything up to this step is step 1. So we move to step 2. Step 2 says wrap both sides of the equation in parentheses and raise both sides of the equation to the power which eliminates the radical. So since here we have a square root, just like we reviewed at the very beginning, how do we undo a square root? By squaring. So here, to get rid of our square root, we need to wrap both sides of the equation with parentheses and square. And so that of course makes the left hand side just x plus 5, and the right hand side becomes a 5 squared or 25. So that right there is step 2. Which then brings us to our third step. Third step says to solve the remaining equation. Solve the remaining equation. So if I wanted to do that, I would need to subtract 5 from both sides. When you subtract 5, you're left with x equals 20. Not much to the third step. Sometimes there's more to it, but for this particular one, that's it. And so the last thing we have to do with any of these is once we've actually solved, we need to check for what we call extraneous solutions, which are basically solutions that don't work. And this usually happens when the resulting equation is not a linear one like this, but a quadratic equation. Because you'll recall with quadratic equations, we usually get 2 answers. And so here we only have one answer, and it's probably going to be good, but we'll get in the habit of checking anyway. So this is our last step. We are going to check our answer. So we're going to do a check here. So when we check, notice that we are checking in the original equation. So I'm going to take my 20 and I'm going to plug it back into the original, which is going to look like this. It's going to look like 8 times the square root of 20 plus 5. We have a minus 12 equals 28. So we can go ahead and simplify inside the radical. That's the square root of 25, which is of course 5. So we have 8 times 5. We have the minus 12. 8 times 5 is 40, and 40 minus 12 does equal 28. So does our answer check out? It absolutely does. So our final answer is x equals 20. Okay, so that's one of these. Now this one required a bit of simplifying to isolate. That was where most of the work was at. Let's take a look at another one. Example B here. Again, what should our first step be? We're trying to solve example B for x. Should be to isolate. So if I subtract 5 from both sides, that's going to give me the square root of x plus 2 on the left side. And on the right hand side we get negative 5. So are there any problems with where we're at so far, or are we good to go? I'm hoping that you noticed that this can't be negative. There never exists any number that you could take the square root of and get a positive. This is not possible. So in this case, our answer is no solution. We can't have a square root be negative. Just keep that in mind. Whenever you, just like with absolute values, they can't be negative. Well, the result of a square root can't be negative. If we move on to the third one, notice we already have one of our radicals isolated, so we don't need to do any isolating. However, that brings us to step 2, where we need to get rid of the radical. And in this case, we have a cube root. So how do we get rid of a cube root? We don't square it. What do? We cube it. So we cube the left side, we cube the right side, and when we cube the left side, the cube gets rid of the cube root, leaving us 3a plus 4. And then on the right hand side we have 2a plus 7. And so we got to solve, get all the a's on the left hand side, subtract 2a, which means the 4 has to go to the other side, so we subtract 4. And that leaves us with 3a minus 2a is a, and 7 minus 4 is 3. We get an answer of a equals 3. You recall we need to check, so if we do our check here, we have the cube root of 3a, but a was 3, so we have 3 times 3 plus 4. That should be equal to the cube root of 2 times 3 plus 7. 3 times 3 is 9, plus 4 is 13. On the other side, 2 times 3 is 6. 6 plus 7 is also 13. So it does check out. 3 is our correct answer. Hopefully that makes sense. So this brings me to my fourth and probably most difficult example here. And on first appearance, this problem appears different from the last ones because we don't have a radical. And I'm hoping you recognize, though, that this 1/2 power right here actually means square root. Remember that x to the 1/2 power means the same thing as the square root of x. Hopefully that looks familiar to you. So really, probably our first thing we should do here is just rewrite this problem so it's something we're more familiar with. X plus 7, the square root of x plus 7 minus 5 equals x. And so now we're back to what we're used to doing. We need to isolate. We're going to add 5 to both sides. And when we do that, we end up with the square root of x plus 7 equals x plus 5. Negative 5 on the left-hand side becomes a positive 5 over here. And this is where the problem gets more difficult, because now when we go to square both sides, one thing we need to talk about is what is the square root, or what is x plus 5 squared. And so that of course is x plus 5 times x plus 5, which is equal to x squared plus 5x plus 5x plus 25, which is equal to x squared plus 10x plus 25. So that right hand side is now a lot more complicated. The right hand side is x squared plus 10x plus 25. And then the left hand side, of course, the square root is now gone, so we have x plus 7. And so here we now need to be able to recognize that this is not a linear equation where we try to get the x's on one side and numbers on the other. Here we actually have a quadratic equation. And so we need to do what if we have a quadratic equation? Hopefully you're thinking in your head that we need to get everything on one side set equal to 0 so that we can factor. Remember we did that in the section 8.4, and so I need to move that x over by subtracting x, and I need to move the 7 over by subtracting 7. And so this allows us to have 0 equals x squared. 10 minus x is a positive 9x, and then 25 minus 7 is 18. So then once we have everything set equal to 0, what do we do next? Well, the only way that we've talked about in this class so far solving this is by factoring, so we can write it as a product. We're looking for two things that multiply to give us 18, but add to give us 9. So you remember 18 we could think of as 3 times 6, we could think of as 2 times 9, and if we're trying to add to get 9, we're probably going to use the 3 and the 6. So this is going to be x plus 3 and x plus 6, which then we have two solutions that are going to arise. We have that x plus 3 has to equal 0, or x plus 6 has to equal 0. On the first one, if we subtract 3 from both sides, we get x equals negative 3. And on the second one, if we subtract 6 from both sides, we get x equals negative 6. And so now we have these two answers. And what's our last step? What's the thing we have to do last once we've found some potential answers? We need to check. And we always check not in like this equation, but in the original. So we need to take negative 3 and plug it in. Plug negative 3 in everywhere there's an x. And so here we see that square root of negative 3 plus 7 is the square root of 4. Square root of 4 is 2. And 2 minus 5 is equal to negative 3. So the first one checks out when we have x equal to negative 3. We do the second one here. We could check x equals negative 6, and we plug that one in. We have negative 6 plus 7 minus 5 equals negative 6. Negative 6 plus 7 is 1, so we have the square root of 1 minus 5, which is 1 minus 5, which of course is negative 4, and negative 4 is not equal to negative 6. So that one does not work out. So we're going to cross out. This is an extraneous solution. We don't want to include that one in our solution set. We're just going to have one answer. It's the answer x equals negative 3. So that pretty much covers the gamut on solving radical equations. We now need to move to some applications of radical equations. And so if we're trying to solve different applications, sometimes we need to do what's called solve a literal equation. That's where we take an equation like a equals L times W, and we solve for one of the variables that hasn't been solved for. For example, we might want to take that equation and solve for L. The way we would do that is by dividing both sides by W. So if we took, you see it right here below, but if we took A equals L times W and divided both sides by W, that would get rid of the W's, and it would give us exactly what you see here, that L is equal to A divided by W. And sometimes it turns out that these equations or these formulas are formulas that involve radicals. And so that's what we see here in this first equation. This first example says, take this literal equation and solve it for A, and you notice A is inside the radical. And we know how to get rid of radicals, though. We get rid of radicals by squaring and cubing and things like that. So let's think about how to solve this one for A. What's our first step if we're solving radical equations? Hopefully you said that we need to isolate the radical, and the way we do that in this case is we would subtract 2 from both sides. So if I do that, the left-hand side becomes r minus 2, and that's equal to this cube root of 3a divided by t. Now what's our next step? Next step is to wrap both sides of the equation in parentheses, and because it's a cube root, we have to cube. So then our equation becomes r minus 2 cubed equals 3a over t. Notice we're still trying to get the a by itself. So now we could take and multiply both sides by t. Get rid of our denominator here, which gives us t times r minus 2 cubed equals 3a. And we still don't quite have a by itself. Our last step is to divide by 3. So we end up with that a, that's by itself, is equal to t times r minus 2 cubed all over 3. So that's what we call solving a literal equation for a variable. So let's take a look at a little bit more of an interesting example. It says the period of a pendulum is the amount of time it takes to swing from one extreme to the other and back again. So the period capital T of a pendulum in seconds can be found by this nice formula here. And we're asked, and then we're told that L is the length of the pendulum, so how long that pendulum is. a pendulum has a period of 1.2 seconds. By the way, if you don't know what a pendulum is, which could be the case, a lot of times they happen on old grandfather clocks. You have this clock with a hour hand and a minute hand, and it has this little case down below, and usually there's this arm that extends down with kind of like a little ball at the end, and it swings back and forth, and that's what helps keep the time. It keeps the seconds by the ticking and stuff. So the period is the time it takes to swing from one side and back to the same spot. And then L would be how long the pendulum arm is. So this right here would be L. Hopefully you can picture that a little bit better now. So in this example it says the pendulum has a period of 1.2 seconds. So they're telling us that T, that's the period, is 1.2 seconds. And it says to find its length. We want to find what L is. And it gives us some directions for rounding. So notice, to be able to do this, in our original equation, L is right up here. L is inside the radical. So we have to be able to solve the literal equation. We have to be able to take T equals 2 pi times the square root of L over 32, and we have to solve for L. So if I want to do that, I of course first need to isolate the radical. I need to divide both sides by 2 pi, which gives us T divided by 2 pi equals the square root of L over 32, because the 2 pi's cancel. And then we got to get rid of the radical, so we of course square. Which gives us T over 2 pi squared equals L over 32. And lastly, to get that L by itself, we multiply both sides by 32. So we multiply by 32. 32's cancel, and we get L equals 32 times T over 2 pi quantity squared. And so you could put this, now we could solve for L because we know what T is. T is 1.2 seconds. So our particular equation has to be 32 times the period, which is 1.2 seconds, divided by 2 pi quantity squared. We could go ahead and use the calculator to calculate this now. So we're going to take 32 times, in parentheses here, 1.2 divided by, I'm going to put this 2 pi inside of parentheses because we need to divide by 2 and by pi. So the parentheses forces the 2 pi to be in the denominator. And we're going to raise that to the second power. We're going to square it. This comes out to an answer of 1 point, we're supposed to round to the nearest hundredth. So that's 2 decimal places. So this is going to be 1.17 feet. That's our final answer. If the period of a pendulum is 1.2 seconds, that means its length has to be 1.17 feet. So you should be able to go ahead and do your self-check now. We got a couple here of solving extraneous, or solving for radical equations. Please make sure that you check for extraneous solutions. And there's one of these application problems that's kind of interesting. It has to do with how police officers tell how fast a car was traveling based on the length of a skid mark. So thank you for your time. We'll see you in class.